This video demonstrates the use of infrared spectroscopy, also known as IR. IR is used to assist in identifying functional groups in organic molecules. Before you can run an IR spectrum, a background must be run. The background takes an IR signature for the molecules present in the atmosphere.
Before you run the background scan, make sure there is no liquid or solid on the IR window.
This is how you run the background. Click the measurement button on the left corner of the screen. From there, you have two options. Click Start Background Measurement to start the background scan.
Once it tells you that it is finished, you can load the sample. To load the sample, place one drop on the window. Note, always remember to wear gloves. Now you can click Start Sample Measurement.
If you wanted to continue through all 24 scans, click Start Measurement on the bottom left corner of the screen. Once all scans have been completed, change the display from absorbance to transmittance using the button on the left. To adjust the y-axis, click the Scale button on the top menu. If you want to do peak picking, click the Evaluate tab on the left corner of the screen and click Peak Picking. Peak picking shows you the wave numbers for each peak.
If your spectrum does not show all the wave numbers you want, choose the arrow besides peak picking and choose Interactive Peak Picking. In order for it to work, right-click somewhere on the spectrum and left-click on the cursor so you can change the threshold. If you want to print your spectrum with the labels, click Store.
You can now print your spectrum by checking the Print button and clicking Go. The Unload button should also be checked so that the display is cleared for the next person.
After you have finished taking your spectrum, remember to properly clean the IR for the next student to use.
This is our printed spectrum. The amount of light transmitted is plotted on the y-axis, and the frequency in units of cycles is plotted on the x-axis. The peaks on the spectrum help us to identify the different functional groups in the molecule. Each peak is associated with a different wave number. These wave numbers correspond to the energies needed to stretch and bend the bonds of the molecule in question.
This video is about the reliable verification of known materials. ATR is suitable for a wide range of sample types. For an easier handling of liquid samples, we now use an ATR unit with a sample trough. The start of any FTIR analysis is a background measurement. Before, make sure the crystal is clean and use rubbing alcohol and soft tissues if cleaning is necessary. When ATR is used, liquids and oils are directly applied to the crystal. Assure your sample covers the diamond entirely and apply the pressure stamp only for solids. The preview spectrum indicates the quality of contact between diamond and sample. It should already display the sample spectral fingerprint well above the baseline. Search the list of reference compounds for the material you want to verify and select the according compound from the drop-down menu. After the substance is selected, you can start your verification. The measured sample spectrum automatically will be compared with all reference compounds in the evaluation method. In this example, we successfully verified the liquid as glycerol. After the analysis, you can take a closer look at the measured and reference spectrum, print a report, or just continue to verify your next sample. Just repeat the previous steps. First, clean the crystal, then apply the sample, and lastly, select the appropriate substance. FTIR is a standard technique to ensure the correct chemical identity and quality of raw materials and products. It is used in virtually any manufacturing industry worldwide to control the quality of incoming goods and final products. Thanks for watching, see you next time. Welcome to the Principles of Infrared Spectroscopy. Let's get started right away with probably the most important question. What is infrared spectroscopy? Basically, infrared spectroscopy studies the interaction between infrared radiation and matter. We might end this presentation right here, but you may ask, what is infrared radiation? Well, infrared is a particular part of the electromagnetic spectrum that has a longer wavelength than visible light. A longer wavelength means the light carries less energy. A longer wavelength also means a smaller wave number. Since infrared spectra are mostly labeled in wave numbers, wave number is a term frequently used throughout this tutorial. All infrared spectroscopy is not created equal, as it can be subdivided depending on wavelength into near, mid and far infrared, although mostly mid-infrared is meant when the term IR spectroscopy is used. As mentioned before, infrared light interacts with matter. But how exactly? Well, first infrared light passes the sample, in our case an exemplary water molecule. Depending on the energy levels, this light can trigger vibration in specific molecular bonds. This is called absorption. There are different kinds of vibrations, but the most prominent are the symmetric stretching vibration, the anti-symmetric stretching vibration, and the deformation vibration. Others are rocking, wagging, and twisting vibrations. The energy absorbed by the molecule is consumed and is therefore missing from the original IR beam. But how can we use this principle to our advantage and investigate this interaction? First, we need infrared light from a fitting source. The light is then directed at the sample. Some light is going to be reflected, but a larger fraction will travel through the sample and specific parts of it are going to be absorbed by the sample material. The part of the light that is transmitted and carries the molecular information of the sample can then be collected by a detector to produce an electronic signal. But how do we turn this electronic signal into a spectrum? Well, this depends on how the infrared spectrometer is set up. In its early days, infrared spectra were exclusively acquired by traditional dispersive IR spectrometers. This was done by directing light onto a diffraction grating that splits the light into several single beams. Afterwards, these beams were directed at the sample and each wavelength individually examined. With the rise of improved electronics and CPU processing power, Fourier transform infrared spectrometers superseded these traditional instruments because FTIR spectroscopy offers significant advantages. It has an improved signal-to-noise ratio, it is a lot faster, and it shows superior wave number accuracy when laser calibration is applied. But how does an FTIR spectrometer differ, and how does it work? At the heart of the FTIR spectrometer is an interferometer. Shown on the right is a Michelson-type interferometer. During the measurement, the IR beam enters the interferometer and is directed at the beam splitter. As the name suggests, this splits the beam into two separate beams that are directed at a fixed and moving mirror respectively. Then the light travels back to the beam splitter, where it is recombined, causing interference, and is then directed at the sample material. That way, the spectral information of all wavelengths can be acquired simultaneously, saving a lot of time. At the end, the detector produces a raw signal of light intensity versus mirror position. But how do we get from here to the classical infrared transmission spectrum? To get nice and clean sample spectra, we have to get rid of the environmental influences that may show in our spectra, like carbon dioxide or water vapor. To do that, we first need to measure a spectrum without a sample present. This raw signal is then mathematically Fourier transformed into the classical IR plot of light intensity versus wave numbers. We now have a single channel reference spectrum. Then we insert the sample into the beam path and repeat the procedure. Fourier transformation then yields another single channel, but this time it's a sample spectrum. Then we only have to combine both spectra by dividing sample spectrum by reference spectrum, and then we have the classic view of an FTIR transmission spectrum. But what can we do with it? A lot of things, actually. An FTIR spectrum is like a chemical fingerprint. This enables chemical identification of a variety of samples and is frequently used to characterize material properties and verify known and elucidate unknown samples. It is utilized by many industries, but is especially useful whenever chemical information needs to be obtained straightforward in a short amount of time. FTIR is extremely versatile depending on your spectrometer setup and measurement technique used. Various applications are feasible and many different analytical questions can be answered. Thanks for watching, and if you want to know more about FTIR spectroscopy, take a look at our hands-on tutorials.